The twinkling firmament around us is made up of billions of stars, each more luminous than the last. But despite their age, do all these stars of the celestial vault share the same fate? What exactly do we know about their evolution? And have we unraveled all the mysteries surrounding these stars that so often transport us into daydreams? Dear traveler, welcome. Today we're setting off on an exceptional stellar expedition, which will take us up close and personal to a certain type of strange and disconcerting star. These are stars with extraordinary behavior, located in regions where we least expect them. Thanks to their insatiable curiosity, we were able to lift part of the veil concealing these unlikely stars, known as vampire stars. In the course of our journey, we'll gradually learn the origins of this sobriquet, which is as singular as the stars it describes. We'll also discover that the stars that populate our galaxy and the entire cosmos are not as similar as we might think at first glance. But before we begin this new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Whether in literature or more recently in film, there are many stories, more or less bloody, recounting the adventures of evil blood-drinking creatures, vampires. These legendary monsters have been described in many ways across the ages and continents. Dracula, the famous character born from the pen of Irish novelist Bram Stoker, is still part of the imagination. However, the quest for eternal life that these fanged monsters covet has found an echo in the cosmos. Some stars, despite the laws of astrophysics, seem to have found a way to offer themselves a second life, if not eternal existence. These are the so-called vampire stars, better known as Blues Stragglers. These vampire stars, found mainly in globular clusters, shouldn't exist. At the very least, they should have the appearance of their many neighbors, old stars that have lost their luminosity, namely red giants. But it turns out that these blue stragglers, unlike many of the surrounding stars, are blue, hot, and massive. How is this possible? Could they be stars from the galactic disk that have migrated through a gravitational interaction mechanism towards a globular cluster? Or could it be that these stars have fallen behind their fellow stars, as if they had found their elixir of youth? That's what we'll try to elucidate in this video. But you probably already have an idea of what we'll be observing over the next few minutes. If you haven't, the names of these strange stars should provide you with a sufficiently eloquent clue. Before we start making comparisons, I suggest we take a closer look at the life cycle of an ordinary star. The first stage in a star's life is its birth, or more precisely its formation. This occurs when a cloud of gas and dust, in other words, stellar matter, collapses in on itself. Of course, depending on the primary composition and mass of this cloud, the star in the making will evolve in different ways. Some will never go beyond the brown dwarf stage, while others, benefiting from abundant raw materials, will go so far as to create a black hole after a very long process and complete collapse. During the very first phase of transition, which can last several thousand years, the fall of gas towards the center of the cloud, due to gravitational energy, heats up the star in the process of formation. The pressure produced by the heat slows the contraction, and the star glows like a glowing ember. On the other hand, if the star's mass is less than 8% of the Sun's, its hydrogen cannot fuse. However, the heavy hydrogen present in the universe allows this brown dwarf star to shine minimally among its contemporaries. The next passage begins the main sequence of a star's life cycle, a crucial and relatively stable stage in its existence. The duration of this phase depends greatly on the type and size of the star concerned. The main sequence represents the period during which the star shines by converting hydrogen into helium in its core through the process of nuclear fusion. This process depends on the star's size, mass, and composition, but on average occurs when the star's core reaches a crucial temperature of around 10 million degrees Celsius, or 18 million degrees Fahrenheit. At these extreme temperatures, nuclear reactions become energetic enough to fuse hydrogen nuclei, producing helium while releasing a large amount of energy. This energy radiates outwards, creating a pressure that counteracts the gravitational force, trying to make the star contract in on itself. The time a star spends on the main sequence depends on its mass and hydrogen consumption. Massive stars with more available hydrogen will consume their fuel more quickly. For example, our Sun, a G-type star, has been on its main sequence for around 4.6 billion years, and is expected to remain there for another 5 billion years or so. By comparison, a smaller, less hot M-type star could remain on the main sequence for tens or even hundreds of billions of years. Larger, hotter O-type stars will burn through their hydrogen much faster, remaining on the main sequence for only a few million years. Once the hydrogen in the star's core is exhausted, the star leaves the main sequence, inaugurating the next phase of its evolution, which could be that of a red giant or supergiant, again, depending on its initial mass. Throughout the cosmic ages, a star passes through several distinct phases, each determined by the delicate balance between gravity and thermal pressure, as well as by the amount of hydrogen available for nuclear fusion. From the very first moments of its birth, the star begins its life by transforming hydrogen into helium in the heart of its fiery entrails. However, this reserve of hydrogen is not eternal. As the hydrogen is depleted, the star enters a period of transition. During this phase, gravity begins to take over, further compressing the star's core, which in turn raises its temperature. This rise in temperature triggers the fusion of helium into heavier elements, such as carbon, while at the same time causing the star's surface to expand and cool. From there, the star's future is shaped differently, according to its original mass. Red dwarfs, tiny stars with less than half the mass of the Sun, live extremely frugal lives. Their surface temperature remains relatively low, around 3,300 degrees Celsius, and their frugal composition of hydrogen enables them to shine continuously for trillions of years. At the end of this prolonged period, these modest, persevering stars eventually transform into white dwarfs. Then over time, cool and solidify into crystalline spheres of carbon and oxygen. Stars similar to our Sun, with masses between 0.5 and 8 times the solar mass, have a more turbulent life. After exhausting their hydrogen, their cores contract, and the temperature rises drastically, reaching up to 100 million degrees Celsius, or 180 million degrees Fahrenheit. This intense heating initiates the fusion of helium into carbon. They then swell into red giants, colossal entities up to 1,000 times the diameter of the Sun. After ejecting their outer layers in the form of planetary nebulae, they leave behind a hot core that gradually cools to form a white dwarf. Slightly more massive stars, between 1.5 and 8 solar masses, follow varied trajectories, oscillating between cycles of contraction and expansion, fusing heavier and heavier elements in their cores until they reach iron. These complex thermodynamic processes lead to Type II supernovae, from which they may leave behind neutron stars or black holes. For stars whose mass exceeds 10 times that of the Sun, their destiny is often to become blue giants. These massive celestial entities are distinguished not only by their impressive size, but also by their frantic energy consumption. Their great mass means that they burn their nuclear fuel at a frenetic pace, resulting in a relatively ephemeral existence on the cosmic scale, lasting only a few million to a few tens of millions of years. During the blue giant phase, these stars undergo significant transformations. They leave the main sequence after exhausting the hydrogen in their cores, triggering a series of nuclear reactions that convert helium into carbon, and successively heavier elements are formed through nuclear fusion processes. The star continues to expand, its core contracting as its outer layers move away from the center. The ultimate fate of a blue giant is just as spectacular as its life. As nuclear fusion continues, generating heavier and heavier elements, the star's core becomes heavier until it can no longer support its own gravity. At this crucial stage, a cataclysmic implosion occurs, leading to one of the most fascinating phenomena in the universe, a supernova. This stellar explosion releases astronomical energy, briefly illuminating the cosmos before slowly fading away. The remains of these blue giants can then either form a dense neutron star or, if the mass is sufficient, a black hole. If blue giant stars are anything like vampire stars, the presence of the latter in globular clusters, where the star population is very old, raises a question, and it has something to do with the lifespan of blue giants. After all, blue giants are not known for living long. Blue giants, as their name suggests, are among the largest stars we can observe. Their blue color also means that they are the hottest of all observable stars, the others reflecting white, yellow, or even red light when they are at the end of their life, as we've just seen. The high luminosity and extremely hot temperature of these stars is due to the fact that they burn up their resources rapidly without restraint. This means that these stars run out of fuel very early on. For this reason, blue giants have the shortest lifespan of all stars, between 10 and 100 million years, making them quite rare. For the same reason, blue giants mainly reside not far from the star-forming regions where they were born. Among the best-known blue stars are Regulus, the flagship star of the Leo constellation, Spica, and Rigel, the brightest stars in the Virgo and Orion constellations. But the most massive star ever observed is R136A1, located 163,000 light-years from Earth in the Tarantula Nebula. It is at least 265 times more massive than our Sun. R136A1 is an extraordinary star. Initially considered a blue supergiant, it is now classified as a Wolf-Rayet type, WN58 star. In the early stages of its existence as a blue supergiant, R136A1 was characterized by extremely high temperatures and intense luminosity, all wrapped up in a spectacular bluish hue. These massive stars undergo intense nuclear reactions, fusing hydrogen into helium at an accelerated rate. Over time, the substantial loss of mass due to powerful stellar winds and the reduction in available nuclear fuel lead these majestic stars to transition to the Wolf-Rayet stage. Wolf-Rayet stars, like R136A1, display even more powerful and rapid winds, eroding their outer envelopes and exposing their fiery, tumultuous cores, where heavier elements are currently being formed. These stellar winds help seed the universe with a rich diversity of elements, serving as building blocks for future generations of stars, planets, and eventually life. A question is probably emerging in your mind. How can blue stars be found in globular clusters, which, far from being able to produce young stars, are populated exclusively by old red stars? However, blue stars do exist in this type of calm environment, at least on the surface. These are known as Blues Stragglers. These blue stars, which have all the characteristics of young stars during their main sequence, nevertheless evolve, mainly in globular clusters, which are conglomerates of very old stars. Indeed, these clusters, which gravitate in the galactic halo, were probably formed at the same time as their host galaxy, several billion years ago. So how can they be home to blue stars, the oldest of which are only 100 million years old? Are these juvenile-looking stars, located mainly in the center of clusters that sometimes contain hundreds of thousands or even millions of stars, really as young as they seem? Or have they found a subterfuge to extend their lifespan? And if so, to what detriment? That's what we're going to try to elucidate through the various discoveries made about them. The discovery of blue stragglers is a very recent one. It dates back only to 1953. Alan Sandage, an astronomer at the Carnegie Observatories in Pasadena, California, first described this type of star while observing M3, a globular cluster located some 33,300 light-years from Earth in the Hound constellation. While studying this star cluster, which is one of the largest and brightest globular clusters on record at the time, he was surprised to discover it. While carrying out photometry, he noticed in the midst of countless old stars and several dozen variable stars, the presence of an atypical type of star, bright blue and hot. Unlike most of the other stars in the observed cluster, which seem to have a common past and thus to have formed at the same time, the stars discovered left him perplexed. Indeed, the stars in question had all the characteristics of a newly formed star, something that seemed more than unlikely within this globular cluster, whose age is estimated at over 11 billion years. However, these blue stars, which defy the rule of the Hertzsprung-Russell diagram, do exist. This diagram, used to study stellar populations, is in fact a graph showing the luminosity of a set of stars as a function of their effective temperature. But Alan Sandage's recently discovered star type is an exception to the rule, as it doesn't fit neatly into this spectral classification. Indeed, a blue straggler, which is a massive main sequence star, should theoretically not exist in this globular cluster. The scientific community therefore set out to elucidate what it considered to be the equivalent of an anomaly. When and how did such a massive star, 2 to 3 times the mass of the other main sequence stars in its host globular cluster, come into being? As more and more similar stars came to light, several theories began to emerge. The most obvious of these was that the existence of such a star was potentially linked to its period of formation. The latter must have been much more recent than the formation of the cluster population as a whole. However, this explanation failed to convince most astronomers. In fact, these late-forming stars needed large quantities of dust and gas to form. However, the cluster got rid of these residual elements a long time ago, during its formation. The second hypothesis was that this star must be foreign to the cluster in which it was detected. Although spotted in the field of observation of the cluster under study, it might be physically unrelated to it and located on a different plane. In the same vein, another idea has also been put forward. The star may have been torn from the galaxy's disk and captured by the star cluster when it was a little too close to it. These last two theories were not accepted for very long, not least because of the location of these atypical stars within their host globular cluster. Indeed, blue stragglers are essentially located in the most central regions of the stellar cluster that hosts them, implying that their physical integration into the structure has not occurred recently. This possibility is inconsistent with their recent formation. A final theory, dating back to 1964, was based on possible interactions within the existing group of stars. Astronomers Fred Hoyle and W.H. McCrae put forward an identical hypothesis, namely that 2 neighboring stellar mass stars, forming a tight binary system, would have collided or transformed matter and eventually merged, giving rise to this massive, luminous colossus. For several decades, the mystery remained unsolved. Intrigued, many astronomers have continued to study these most massive and ancient groupings of stars in the universe, in search of answers about the formation and evolution of the Milky Way, and indeed of the universe. The 47 Tucanae cluster, one of the largest in our galaxy, is one of the most closely observed star clusters. Located in the Tucanae constellation, around 15,000 light-years from Earth, it is a relatively compact globular cluster, with an estimated diameter of 140 light-years. In 1991, Aided by the Hubble Space Telescope, itself equipped with a high spatial resolution, ultraviolet-sensitive camera, a team of astronomers discovered the presence of several blue stragglers at the heart of the cluster. In their statement, the scientists revealed that they had resolved 21 of them, which they believed to be extraordinarily concentrated in the center. Their location seems to support the hypothesis that these stars are created by collisions, mergers, or close encounters between stars. The fact that they are located within the cluster itself, in its densest and most luminous part, also explains why these massive stars have remained invisible for so long. Indeed, only instruments employing high spatial resolution, coupled with ultraviolet sensitivity, are able to study the compact core of 47 Tucanae and many other groups of stars in greater detail. The use of this new technology has thus opened the door to abundant discoveries. Whereas ground-based images yielded only a few dozen stars in a precise area of the cluster studied, this onboard camera will have enabled the resolution of around 600 stars. Comparing the images obtained by these two techniques enabled astronomers to discover 21 stars that are extraordinarily bright in ultraviolet light. By comparing the luminosity and temperature of these particularly bright stars with a computer model predicting how main sequence stars appear in ultraviolet wavelengths, the scientists concluded that they were indeed blue stragglers. What's more, the high concentration of these specific stars towards the cluster's core suggests that they are relatively much more massive than the vast majority of its component stars. The high mass of some of these stars could also be explained by the presence of binary systems. A considerable population of millisecond pulsars and binary stars has also been discovered in 47 Tucanae, supporting the idea that close gravitational encounters between single stars, binary stars, and even binary systems could well take place in this zone. A few years later, in 1995, another group of astronomers focused on one of these blue stragglers. Still using the Hubble telescope, they were able to observe its behavior. The result, which they describe as exciting, will help to support a number of existing theories on the formation and evolution of these enigmatic stars. After analyzing the star's spectrum and measuring its temperature, radius, and rotation speed, they were able to obtain the star's mass. While its derived temperature and mass are consistent with the specifics of a normal star with a mass around 1.7 times that of the Sun, its speed is unexpected. In fact, it turns out that this blue star rotates 2 to 3 times faster than its counterparts, and 75 times faster than our Sun. All these elements offer scientists the opportunity to understand how blue stragglers are formed. While it is becoming clear that a star of this type is created by the fusion of 2 low-mass stars, it remains to be seen by what process. Was it a violent collision, or a long process of fusion between binary stars, with one siphoning energy from the other? According to the scientists, this second hypothesis produces rapid orbital movements of the binary star, generating, in effect, an accelerated rotation of the pair in the final phase of fusion. Over the years, thanks to cutting-edge technology, more and more blue stragglers have been detected. In a 2006 study, which examined the chemical signatures of 43 of the Blues Stragglers in Cluster 47 Tucanae, 6 of them had lower concentrations of carbon and oxygen than their counterparts. The scientists concluded that their surface material must almost certainly have been literally sucked up from the deep interior of a parent star in a double system. The same researchers also studied these atypical stars in 56 other globular clusters. They found that the amount of blue stragglers in a particular cluster was unrelated to the potential collision rate. Thus, they partly put to rest the theory that these stars were the result of collisions between several stars. Instead, there did seem to be a correlation between blue stragglers and the rate of binary stars in these different globular clusters. This finding enabled them to prove that the majority of blue stragglers, including those closest to the core of these clusters, are indeed the descendants of two binary stars. It took more than 50 years for astronomers to unravel the mystery of these immature-looking yet ancient stars. Among the many stars studied in an attempt to better understand these curious objects, one has caught astronomers' attention for its strange behavior. This is the star SS Leporis, also known as 17 Leporis. Long catalogued as a variable star in the Hare constellation, SS Leporis is in fact a rather unusual binary star system. The two stars revolve around each other in 260 days, and the distance between them is only slightly greater than that between the Earth and the Sun. The largest and coldest of the two stars, a red giant, spans a quarter of this distance. To give you an idea of their proximity, the orbit with its companion could be compared to that of Mercury with the Sun. But above all, this red giant, which is in fact the more evolved of the two, paradoxically happens to be the less massive of the two stars. How could these mass ratios be reversed in such a way? To unravel the mystery of this unusual phenomenon, scientists decided to study the dynamics of the system while observing the most central parts, inaccessible with conventional telescopes. In 2010, astronomers created a virtual telescope 130 meters in diameter, offering a view 50 times sharper than that provided by NASA's Hubble Space Telescope. To achieve this, they combined light captured by 4 telescopes at the European Southern Observatory's Piranal Observatory. While the scientists were convinced that matter was transiting from one star to another in this unusual system, they didn't know how. Their discovery has enabled them to assert that this mass transfer does not follow similar patterns already known. The new, extremely precise observations showed that the red giant is smaller than they had previously thought. Its companion, a blue star, although smaller in size, turns out to be the hotter of the two. Its mass is around 2.7 times that of the Sun, compared with 1.3 times for the red giant. The process by which this star flows matter onto its companion star proves far less easy to explain, especially as no flow of matter is visualized between the two stars. Researchers are beginning to put forward the idea that the blue star, with its highly superior mass, has been vampirizing its imposing neighbor for almost 500,000 years. The notion of a vampire star which feasts long and insidiously on a neighboring star became obvious. The vampire star seems to be sucking not the blood, but the hydrogen in plasma from its neighbor, who thus becomes a victim with a shortened lifespan. Unlike cannibal stars, vampire stars, better known under the scientific term of symbiotic binaries, do not quickly devour their prey. The first cannibal star was studied by the European Space Agency in 2004. Researchers had the opportunity to observe a fast-rotating star. It is a super-dense neutron star just 20 kilometers across, initially 8 times more massive than our Sun. Although its mass is astronomical, a thimble's worth of its material, weighing close to 1 billion tons, its small size has meant that it has been virtually invisible to observational instruments. However, on December 2, 2004, it emitted a sudden and powerful X-ray eruption, revealing itself to Integral, the European Space Agency's International Gamma-Ray Astrophysics Laboratory, and NASA's Rossi X-ray Timing Explorer spacecraft. The measurements confirmed that this was one of the fastest spinning pulsars ever studied, with a dizzying speed of 600 rotations per second, which is gradually accelerating. This frenetic rotation is the result of the absorption of gas extracted from a companion star. When this gas crashes onto the star's surface, it causes it to heat up to a temperature of almost 1 billion degrees, releasing extraordinary quantities of X-rays and gamma rays. In short, it makes short work of its neighboring star, which shrinks irreplaceably. This is why this cannibal star is nicknamed the Black Widow. Even more unusual, in 2015, a NASA telescope caught a cannibal star in the middle of a feast. This is a white dwarf at the end of its life, whose gravity is so powerful that it is capable of attracting and eventually disintegrating a nearby telluric planet. In 2011, still intrigued by this unexplained phenomenon, scientists also turned their attention to the open cluster NGC 188. Located in the Cepheus constellation, 6,680 light-years from our solar system, this cluster features 21 Blues Stragglers, most of whose stars are over 7 billion years old. Detailed observational data from the WIYN telescope at the Kitt Peak Observatory in Tucson, Arizona, were used to analyze and compare the 3 main theories concerning the formation of Blues Stragglers: star collisions, star mergers, or mass transfer from one star to another. Collisions or mergers would be conceivable if the companion stars appeared more massive, which is not the case. The mass of these companions, whose luminosity remains low, can only be determined by observing the Blues Stragglers. These are subject to a gravitational force from the red giants, creating an oscillation during their orbit. By observing the movements of the Blues Stragglers, they were able to determine that 16 of them must have a much more discrete companion. The data collected enabled the researchers to assert that each companion star had a mass about half that of the Sun, corresponding to a white dwarf. But what better way to confirm their assertions than with an image? However, in 2011, the technical means available are not yet sufficient to observe this type of star, whose luminosity is relatively low, especially as it lies close to a sparkling blue straggler. Using ultraviolet wavelengths, a team in 2015 was able to prove that 7 of the 21 Blues Stragglers had a white dwarf as a companion, thus supporting the 2011 conclusions of their colleagues. In her study, she points out that only white dwarfs formed within the last 250 million years can be detected, the others being too cool to be detected and thus confirmed. Among the other Blues Stragglers, 7 showed evidence of mass transfer between stars by other means. All in all, it proves that a quarter of the oldest stars do not evolve into red giants, but turn into Blues Stragglers with surprising luminosity and strange behavior. We now know how Blues Stragglers are formed. Stars that appear bright and fresh alongside many faded stars in ancient clusters. They give themselves a new lease on life by absorbing matter from their companion stars. These are not stars that have migrated or collided, giving rise to a massive bright new star. It's a case of one star vampirizing another, giving itself a second life. Vampire stars are mainly observed in stellar clusters. These groups of stars, which formed more or less at the same time as their host galaxy, are home to the oldest stars. Almost exclusively populated by red giants, they nevertheless shine brightly in our starry skies due to their high concentration. Millions of stars are crammed into an area that in other parts of the galaxy might contain only one star or even none at all. In these spherical clusters, some stars appear far less advanced than the majority. But if these younger-looking stars were the result of collisions and mergers, they would have to show age differences. However, the study of these Blues Stragglers within the same cluster has shown that they all formed at roughly the same time. They are therefore not the result of collisions due to random displacements. Since 2011, scientists have known that they are the result of mass transfer between 2 very specific stars. Let's take a closer look at the process by which these stars manage to rejuvenate themselves. When 2 stars form a binary system, orbiting each other, they evolve according to the same pattern. As the 2 stars age, they gradually evolve into red giants. In the process, their volume increases steadily, until they reach several hundred times their initial size. As they move ever closer together, the distance between them shrinks considerably. Gravitational interactions become increasingly important. Inevitably, the star with the highest mass outweighs its companion star. As its gravitational force is greater, it will gradually absorb the outermost layers of gas, which are only weakly held back by the gravity of the second star at the end of its life. Mass is inexorably transferred from the cooling red star to the star that is gradually regaining its youth. By stirring up the hydrogen fuel, the latter generates nuclear fusion at a faster rate. The hydrogen burns hotter and bluer. The least massive, which ends up completely stripped, retains only its core. It loses its red giant status and becomes an insignificant white dwarf. Meanwhile, the vampire star gains extraordinary mass, and after its rejuvenation, begins to shine brightly. At first glance, she may appear youthful, but her real age is much more advanced, just like those who undergo facelifts. While the mystery surrounding the formation of vampire stars seems to have been solved, studies of them are still going strong. The stars contained in the clusters of each galaxy have yet to reveal all their secrets. All the more so, as these stars are the ancient witnesses of many cosmic formations. But we still have to get them to talk. Eager to learn more about their past, Canadian students from the Department of Physics and Astronomy at the University of British Columbia published a study in 2016. It focused on the formation and evolution of Blues Stragglers in the 47 Tucanae cluster. Knowing that all the stars in the same cluster are at the same distance from the observation site, i.e. the Earth, it becomes easier to compare their apparent magnitude. The students created a color magnitude diagram, which is simply the observational version of the Hertzsprung-Russell diagram. They were able to observe the population of Blues Stragglers in this cluster. Their findings suggest that the existence of these stars, which are too blue in this aged environment, is the result of a number of mechanisms, as well as being dependent on the environment in which they evolve. They began by separating the stars into different populations. In equal numbers, bright blue stragglers and faint blue stragglers, main sequence stars, binary main sequence stars, and red giants. In a second step, the researchers estimated the cumulative distribution of each of these categories along the cluster radius of their diagram. They found that bright blue stragglers are more concentrated in the inner regions, while fainter blue stragglers are much more prevalent in the peripheral zone. What's more, the cumulative radial distribution of bright blue stragglers is not echoed by other populations, making it difficult to link their formation to a specific group of stars. On the other hand, faint blue stragglers and main sequence stars show a very similar distribution, suggesting that a binary system may indeed be at the origin of these atypical stars. In short, the study demonstrated that different mechanisms could lead to the formation of blue stragglers. Interactions between several systems seem to dominate in the central regions, resulting in more massive and luminous objects, while binary evolutions appear to be the most common scenario in the periphery of these clusters, generating fainter blue stragglers. They were also able to conclude that the evolution of blue stragglers at equal mass is similar to that of main sequence stars. While these findings still need to be confirmed by future observations, they nevertheless allow us to learn ever more about these strange and surprising blue stragglers. Again, thanks to the Hubble Space Telescope, 26,000 light-years from our Sun, blue stragglers have been detected this time, not in a cluster, but in the bulge of the Milky Way, i.e., at the very heart of the galaxy. In this congested area, which corresponds to the former hub of our Milky Way, amid countless aging stars, blue stragglers also reside. In 2006, a 7-day survey was carried out. Called Sagittarius Window Eclipsing Extrasolar Planet Search, its aim was to detect hot Jupiter-like planets orbiting very close to their stars. After observing and collecting information on the variability of 180,000 stars in the extremely populated central bulge of our galaxy, the scientists were able to determine that most of them were aging Sun-like stars and cooler red dwarfs. In an area once populated by giant blue stars that exploded as supernovas billions of years ago, however, some stars appeared to be out of the neighborhood. Scientists discovered 42 blue stars that were far too bright and hot for the other stars in the galactic bulge. As you might expect, these are probably blue stragglers. If the existence of such rare stars in this part of the galaxy was suspected, it has now been proven. Until now, this area could not be accurately observed, as younger stars along the line of sight to the bulge made visibility confusing. Of the 42 candidate blue stragglers, scientists believe that 18 to 37 could actually be vampire stars. These stars, although very luminous, are undoubtedly old ladies, between 10 and 11 billion years old. Having vampirized a few companion stars, they have given themselves a much longer lifespan than their fellow stars. As for the rest of the blue stars, they may be genuine young stars or objects outside the bulge. Although scientists believe they have understood how blue stragglers evolve in globular clusters, their observations are not yet complete. Indeed, if one thing is certain, it's that they can never be certain of having fully elucidated the workings of our universe. So vast and constantly evolving is it. Above all, the advent of new, ever more advanced technologies means that discoveries can be made that sometimes drastically call into question past deductions. This is why so many star clusters are constantly in the sights of numerous telescopes. A case in point is the Messier 30 cluster, located in the constellation of Capricorn, some 28,000 light-years from our solar system. Discovered in 1764 by French astronomer Charles Messier, it was initially thought to be a round nebula containing no stars. However, 20 years later, this formation, whose diameter is around 90 light-years, took on the status of a cluster with an indefinable core due to its very high concentration and density of stars. Its spectral study, which classifies it as F3, indicates that it is extremely poor in heavy elements. It is therefore a very old globular cluster in our galaxy, probably 13 billion years old. For astrophysicists, this swarm of several 100,000 stars represents a case study that will certainly enable them to learn even more about the evolution of stars. With the help of the Hubble Space Telescope, astronomers have identified two distinct types of straggler star, just as their colleagues had previously done when studying the 47 Tucanae cluster. In a study published in 2009 by Francisco Ferraro, an astronomer from the University of Bologna in Italy, the hypothesis that blue stragglers can evolve in this way as a result of different processes seems to be confirmed. These stars, which are not as young as they first appear, are indeed the result of stellar encounters. Although their mass is greater than the typical mass of individual stars in Messier 30, they do not all have the same properties, which means that the two formation scenarios already presented are equally valid, but also that they can occur simultaneously in the same cluster. Potential collisions thus lead to the fusion of several stars, which, forced to mix their fuel, fan the flames of nuclear fusion. And as we observed earlier, the evolution of binary systems can just as easily spawn a blue straggler alongside a longtime companion, then devoured on the surface. What's more, by compiling the data collected by the Wide Field Planetary Camera aboard the Hubble Space Telescope, the astronomers found that blue stragglers, although widely scattered within the cluster, are particularly more concentrated near its center than the so-called medium stars that populate it for the most part. They deduced that these blue stragglers are more massive than most of the stars in this structure. Indeed, as Francisco Ferraro explains, more massive stars tend to sink deep into the cluster like a billiard ball sinking into a honeypot. Whatever the process used to bring these stars back to life, they all have one thing in common. Their mass is around twice that of the typical mass of the individual stars in the cluster. To explain this unquestionable concentration in the central region of Messier 30, where interactions between stars are almost inescapable, astrophysicists have developed a hypothesis. They assume that the Messier 30 cluster underwent a major core collapse 1 or 2 billion years ago. During this cataclysmic event, a large number of stars would have been thrown towards the center of the structure, inevitably leading to a rapid increase in their density. As a result, the first family of blue stragglers would have emerged. As a result of these reorganizations, the twin systems would also have been greatly disturbed, inevitably accentuating the vampirism mechanism to which they are highly prone, giving rise to a second line of blue stragglers. In short, the two existing populations of stragglers that populate Messier 30 are the stigmata of the cluster's core collapse, probably 2 billion years ago. For some, this discovery is direct evidence of the impact of star cluster dynamics on stellar evolution. It now remains to be seen whether other globular clusters also possess this diverse population of blue stragglers. The hunt was on for blue stragglers, and consequently for vampire stars. In the years that followed, many researchers set about the task of detecting as many of these stars as possible, also known as cataclysmic variables. In a 2021 publication, Vikrant Jadhav and Anna Purni Subramaniam report on their meticulous census carried out thanks to the Gaia telescope. Launched in 2013 by the European Space Agency, the Gaia telescope offers excellent positional accuracy, making it possible not only to detect blue stragglers in open clusters, but above all, to study them like never before. Studies are now focusing more on open clusters because of the better distinction they offer between stars, as there are fewer of them in the same area, and consequently, they are closer together. The researchers were thus able to study 670 clusters, all over 300 million years old. They were able to identify 868 blue stragglers in 228 distinct clusters. These are mainly found in the most massive and oldest star clusters. They also confirmed that they are mainly located near the center of these same clusters, and all more massive than the extinct stars of the main frequency. Finally, they were able to draw up a detailed inventory of these exotic stars, and even deduce their formation mechanism. According to their study, it turns out that over 54% of blue stragglers are vampire stars that formed by mass transfer, feeding long but surely on their close companion star. 30% of these rejuvenated stars have benefited from a collision with a second star. Finally, 10 to 16% of blue stragglers came into being as a result of interactions between more than two stars. Thanks to this study, we now know a little more about stellar systems. Numerous observations of these blue stragglers are still in progress, notably using ultraviolet imaging integrated into the AstroSat telescope, the first dedicated space observatory, and the Devasthil Optical Telescope at Nainital, both in India. Nevertheless, globular clusters are not being neglected. Quite the contrary, in fact. One of them, the famous Hercules globular cluster, Messier 13, 25,100 light-years away, is one of the most beautiful objects to observe through a telescope from the Northern Hemisphere. It, too, contains numerous blue stragglers. The galactic globular cluster NGC 6256, located in the constellation Scorpius, some 27,400 light-years from our solar system, has also benefited from close observation. In a study published in 2022, scientists reported that it hosts a double sequence of blue straggling stars. Like the Messier 30 cluster, a detailed photometric study of its bulge concluded that it is at a very advanced stage of dynamical evolution, as evidenced by its central segregation of blue stragglers from lighter stars. On the other hand, while Messier 30 reached this stage of evolution around 2 billion years ago, the process in the cluster, located in the Scorpio constellation, seems less ancient. Comparison with collisional models suggests that a short-lived event probably occurred a billion years ago, favoring the formation of a population of blue stragglers as a result of collisions. These represent almost 60% of the total population of the observed cluster. However, examination of the positions of the two brightest blue stragglers indicates that the cluster may have undergone an even more recent recollapse, as recently as 1 million years ago. While the vast majority of their fellow stars bear the scars of nearly 12 billion years of existence, these stars give the impression of having recently returned to their adolescence. But this hypothesis will require further study before it proves to be correct. These extremely youthful stars may, after all, be the result of collisions generated by evolving red stars. However, this explanation, though possible, remains weak in the eyes of the specialists. While observing the blue stragglers across various clusters, a group of astronomers led by Professor Ferraro of the Department of Physics and Astronomy at the University of Bologna noticed another peculiarity. They found that some of these puzzling objects form by mass transfer in binary systems, triple systems, and sometimes by stellar collisions, and thus having different structural characteristics, preferred certain environments to others. Their discovery, published in May 2023 in Nature Communications, is conclusive. Young blue stragglers prefer calm environments. The scientists were interested in blue stars with rotational speeds in excess of 40 kilometers per second, or 25 miles per second. Of the clusters studied, all of which are very old, 4 have a low density. These are Messier 4, Omega Centauri, Messier 55, and NGC 3201. The 4 other clusters selected for this observation, which are in contrast very compact high-density clusters, are 47 Tucanae, Messier 30, NGC 6397, and NGC 6752. These groupings of stars, with their different structural characteristics, provide a fantastic laboratory for analyzing the behavior of 320 blue stragglers in 2 contrasting environments. These newly formed stars, either through stellar collision or vampirism, start spinning very fast at the beginning of their rebirth, transforming themselves into veritable cosmic spinning tops. But inevitably, this speed gradually decreases. This is why rotation speed is an essential diagnostic tool for distinguishing newly created blue stragglers from older ones, which inevitably exhibit slower rotation. Following their observations and a survey of the fastest rotating vampire stars, the scientists concluded that fast-rotating blue stragglers are more likely to be found in low-density clusters. In fact, 40% of blue stragglers observed in low-density clusters rotate at high speeds, compared with just 3 to 4% in high-density clusters. So researchers who had previously expected to make the opposite discovery, thinking they'd find more fast-spinning blue stragglers in high-density clusters, were extremely surprised by their findings. It opens up a new avenue of exploration for them to try and understand the dynamic processes that characterize the evolution of these vampire stars in different environments. This discovery is likely to have a profound impact on their understanding of the evolution of star clusters, as well as on the consequences of binary systems and stellar collisions. In the course of their observations, scientists are sometimes surprised to discover rare phenomena they may have suspected existed, but had never before had the opportunity to see with their own eyes. For example, they witnessed a super-explosion at the heart of a vampire star system. The super-explosion was detected in 2019, when they carried out yet another search of the countless archives of NASA's Kepler spacecraft. Kepler was designed to find exoplanets by searching for stars that gradually darken as a planet passes through their bright firmament. This technique is therefore ideal for detecting other transient astronomical phenomena, i.e., objects that experience fluctuations in their luminosity. This is how they discovered that Kepler's archives contain some rather unusual data, showing a super-explosion within an unusual binary system. This system consists of a white dwarf star and a brown dwarf, orbiting its companion star every 83 minutes, just 400,000 kilometers apart, roughly the distance between the Earth and the Moon. Because of this close proximity, the white dwarf's intense gravity sucks matter from the brown dwarf. This torn-off material gradually feeds the accretion disk, which spirals toward the heart of the white dwarf. As luck would have it, Kepler was observing in the direction of this system when a very intense phenomenon occurred. He was able to record a superflare coming from this binary system. It brightened by a factor of 1,600 in less than a day, before slowly fading away and then dying out. But that's not all. With Kepler collecting data every 30 minutes, every detail of this massive explosion could be studied. While theories suggest that such an increase in brightness is sudden, the phenomenon in question proved the opposite. In fact, a slow increase in luminosity was observed before the explosion actually took place. Why this slow start? It remains a mystery to this day. According to current theories, this super-explosion could take place when the accretion disk reaches a tipping point. As it accumulates matter, it also gradually increases in size. When its outer rim comes into gravitational resonance with the brown dwarf, this would lead to thermal instability. The disk would then overheat, triggering the super-explosion. This theory makes perfect sense when we compare the temperature of the accretion disk at the different stages immortalized by Kepler. The accretion disk, whose usual temperature is barely 5,000 degrees Celsius, or 9,000 degrees Fahrenheit, would have reached 11,700 degrees Celsius, or 21,000 degrees Fahrenheit, at the height of the super-explosion. It remains to be seen whether Kepler's archives contain any other events of this type, however rare, that would support this hypothesis. As you can see, nature never ceases to surprise us, each time revealing only a tiny part of its mysteries. Among the many other astonishing discoveries, one of them concerns the HR 6819 system. In 2020, a team of astronomers from the European Southern Observatory thought they had discovered the nearest black hole to our Milky Way, accompanied by a star in this system. Shortly after publication, however, colleagues from an international team based at Belgium's Dutch-speaking University of Leuven challenged this original study. According to them, this system does not contain a black hole, but is a two-vampire star system in a transitional stage, extremely rare to observe, although not marginal on the scale of the universe. To unravel this mystery, the two teams agreed to join forces. After agreeing that there were indeed two sources of light in this system, they turned their attention to how far apart they were. Are they two stars orbiting each other in a confined space, or two stars relatively far apart? Thanks to data collected by the Gravity and Multi-Unit Spectroscopic Explorer instruments on the European Southern Observatory's Very Large Telescope Interferometer, they were able to confirm that these two light sources are very close together, only a third of the distance separating the Earth from the Sun. What's more, they believe they witnessed the immediate consequences of a vampire star attack. Indeed, as one of the two stars was stripped by its companion, the latter began to spin much faster than before. The astronomers, lucky enough to have been able to capture this brief post-interaction phase, intend to take a closer look at this vampirism in action. Perhaps they will finally be able to understand how this phenomenon affects the evolution of massive stars, and de facto, the formation of their associated events, such as gravitational waves and violent supernova explosions. And as a result, another mystery remains to be solved. Where does the black hole closest to our Earth hide? To date, astronomers have counted over 1,000 cataclysmic variables. The two stars in this type of system are inevitably close to each other, so that the white dwarf is able to suck matter out of its donor star. But only a dozen of these duos have orbital periods of less than 75 minutes. In 2022, Kevin Burge of MIT's physics department published in the journal Nature that he had spotted one of these cataclysmic variables 3,000 light-years away, in the direction of the constellation Hercules. The two stars in question are so close together that the orbit, which takes just 51 minutes to cover, is the shortest ever observed for a cataclysmic variable. This duo, named ZTFJ 1813 plus 4251, is therefore after a very long life of nearly 8 billion years in full transition. The white dwarf, whose diameter is around 1.5 times that of the Earth, and whose mass is approximately 56% more massive than the Sun, looks rather strange compared to its companion, which is a star similar to our Sun on the verge of becoming a red giant. Above all, scientists have discovered that the vampire star has finished absorbing its neighbor's hydrogen and is beginning to strip it of its helium. This infernal duo is therefore in the process of switching from hydrogen accretion to helium accretion. While they were aware of the existence of cataclysmic hydrogen and cataclysmic helium variable populations, the process by which these stars switch from one to the other was not yet known. Their simulations predict that in approximately 70 million years, the two stars will be so close that their orbital period will be reduced to 18 minutes. The duo will then become a cataclysmic helium variable. They have thus clearly identified the missing link in astrophysics that could explain this transition. When the two stars are close to each other, the inevitable will happen. They will merge and explode, putting an end to the emission of gravitational waves. After this nova, will calm return to this part of the cosmos? And if so, for how long? Unless a black hole appears. During this sudden event, in which both stars are subjected to incredible convulsions, the outer parts of the hydrogen layer and many fragments of the molten products are literally ejected into interstellar space. Depending on the mass and composition of the two stars forming this pair, their evolution may differ. Cataclysmic variables are classified into several distinct groups, often named after the archetype of a bright star with the same characteristics. These include Geminorum variable stars, magnetic or polar cataclysmic variable stars, intermediate polar variable stars, AM Canem, Venaticorum variable stars, and SW Sextantis variable stars. The former, also known as dwarf novae, undergo large explosions caused by deformations of the accretion disk when their rotation enters resonance with the orbital period of the companion star. As for magnetic systems, most of them feature strong variable polarization. Intermediate polars show a partially destroyed accretion disk, while polars prevent the formation of an accretion disk. For the moment, however, the most spectacular phenomenon ever studied is that which causes the vampire star to self-destruct during a supernova. When the accretion process lasts long enough, it leads the white dwarf, the vampire star, to reach the Chandrasekhar limit. The Chandrasekhar mass corresponds to the maximum electron degeneracy pressure an object can withstand, without undergoing gravitational collapse. To the extent that the white dwarf exceeds this limit, the increasing internal density causes the carbon to melt abruptly. This leads to a Type 1a, or thermonuclear supernova explosion, which is fatal. The vampire star, having been too greedy, undergoes a cataclysmic explosion, leading to its disintegration. After shining like no other of its many neighbors, it disappears forever from the cosmos, leaving only the remnants of its explosive end of life. Our interstellar journey is coming to an end. As you've already seen, vampire stars are fascinating asteroids that reveal many secrets about stellar evolution. By observing these binary systems, where a white dwarf relentlessly sucks matter from its more massive companion, called the donor, astronomers can study the different phases in the life and death of these strange stars. These stars, whose activity consists of sucking up matter from their nearest neighbors, are also the source of spectacular phenomena, such as novae, supernovae, and even gamma-ray bursts, which enrich the universe with chemical elements. Thanks to space telescopes and ground-based instruments, scientists have detected numerous vampire stars, mainly at the heart of the oldest stellar clusters encircling our galaxy. These stars, with their unlimited appetite, demonstrate just how dynamic and relatively complex the cosmos is, where matter circulates between stars in a variety of sometimes extraordinarily surprising interactions.